So good afternoon. Oh sorry, it's still the morning. Wow. I guess I'm being a little crazy. I remade the 8-1. I think it was way clearer on how I explained how to do it. The last few you got to do yourself. Just try your best. Look in the back of the book. I did just about all of them for you. So we get to just focus on one with population means. That's what it's saying. Hypothesis testing with population means. I'm assuming we're doing one for uh proportions, one for means and one for standard deviation. So that's how eight's gonna go. So I'm gonna share my screen and get into it. So I'm in intro to stats. I'm up to 8-2. There's some problems to try. Let's go to the book. My Math Lab and Mastering. And I'll do my best to make this clear. But at least we get to do some real stuff finally, which is nice. Hopefully the last video was good. Why did I make it twice? Because I made a mistake. And I didn't want you guys to watch me struggle for a half hour trying to remember how to do it. All right, so we're gonna go to eText, Pearson eText. I'm gonna go to 8-2. Beyond the basics, here it is. Oop, here it is. All right, so this section describes complete hypothesis testing procedure for a claim about a population proportion. We will illustrate hypothesis testing with these three methods. We're going to do the p-value method, where basically we let the computer do it, the critical value method, and the confidence intervals. That's cool. 8-5, pretty sure we don't do, yeah, we're not going to do 8-5. So all this bootstrapping stuff, we're not going to do, but notice that sometimes you have to mess a lot with your data in order to do it. So there's different methods for testing a claim about a population proportion. Part one is based on using the normal approximation to a binomial distribution. This method serves well as an introduction to basic concepts, but it is not a method used by professional statistics. So obviously we're going to use technology for most of it. I'm assuming the first part is just how do we do this by hand, which I think is really important. So here's a hint. When using technology for hypothesis testing, we must usually enter the sample size n, the number of successes, but in real applications, the same proportion is often given instead of x. The number of successes x can easily be found by doing, oh, see, this is what I've been doing. Yeah, I've been doing the total times the percentage to get the value, which is nice. Okay, cool. I just want to make sure some students were having a hard time getting it in the course, so I added a new student. But yeah, so let's keep it going. When conducting hypothesis claims, we get slightly different results. Oh, okay, because we round. Okay, so the results will be a little different. So here's the normal approximation method. The box below includes key elements for testing a claim about population proportion. We need the size n. As long as this is large enough, we can do it, or if it's normal distribution. So remember, every time we're doing this stuff, we have to have a big enough value, or if it's a normal curve. So when testing methods about proportions and critical value are equivalent to each other, they both lead to the same conclusion. This is like kind of thing I showed in the last video. So the p-value, the critical value will definitely be the same thing. They're using the same standard deviation based on claim proportion p. The confidence interval method could result in a different conclusion. So they're recommending we use the p-value method for the critical value testing about a claim of proportion, see exercise 34, but use a confidence interval to estimate the population proportion. Okay. All right, so here's our crazy formulas, and we're going to get into it. All right, so we're in 8, intro to stats, 8.2, and we finally get to start. So remember, this is all about population. So remember, this is using what? We're going to be using z-scores and z-stats. All right, so here we go. And is the sample size still? This is the sample of the proportion. that's how many people was right over that. This is the population proportion. So this is like yes or no. And the Q again is the 1 minus Q, 1 minus P. So this is like yes, what we want, and this is our no group. This we can kind of think about as the percent of people. That's what those mean. All right, so this is what we have to need. It's got to be simple random, fixed number of trials. They have to be independent, so we're asking people yes or no, or heads and tails, stuff like that. Each trial has two categories, success or failure. Probability of success remains the same. So heads or tails 50% every time. The conditions, the conditions n times p is greater than 5. So what does that mean? We need at least, so it's got to be simple random, independent, and we also need 5 yeses and 5 nos. Okay. So the binomial distribution of the sample proportions can be approximated by, okay, so our mean is the number of people times p, and our standard deviation is the square root of n times p times q. If this requirement is not satisfied, we're not going to do the bootstrapping method. And here's this thing. I feel like I've done this formula a million times to get our z statistic. So the percentage from our sample, percentage from the population over P over Q times N. Ta-da! The p-values are automatically provided by technology, or we could use the standard normal distribution curve. I remember I showed it like 3 ways in the video I deleted, but I got all mad. So we're gonna use technology, or we can use 8-3. We want to use 8-3. I can show you that. Okay, so if we want to use 8-3, we'd go here. And we're going to go down to where it says 8-3. And that's in the appendix. Appendix 8 for tables. And this is 8-3 for critical values, but we don't want the critical values. Table 8-2. Yeah, that's the one we want. So here we go. So this is the one to the left, and then we have one to the right, but this is a way we can use our z-scores. So whether it's like, let's say our z-score is negative 1.01, negative 1.01, ta-da, here's our z-score. Negative 1.01 is 1.1562. But StatCrunch does the same thing. Okay, StatCrunch will do the same thing. So we will get the same exact value if you go, oops. We will get the same value. You'll see we can get the same value if we go to StatCrunch for any one of these. So let's say we wanted negative 2.00. Okay. So how can we do that? We can go to I'm being a forgetful human. So stat calculator normal. There it is. Stat calculator normal. Mean zero, standard deviation is 0.1. And let's say our value was negative, what did I say? Negative 2.0. Negative 2.00 should be 0.0228. Negative 0.023. On the wrong side of the table. We think negative 2.00 should be 0.0228. And we got 0.022, yeah, 75, so 0.0228. So you can just use this if you hate the table, right? It's up to you. All right, let's keep it going. Just want to show you that it works. Okay. Oops. All right, so let's see if we have a problem for us to try. Cool. All right. So we have 926 internet users, 50% said yes. Okay, so here we go. This is more, they are independent is yes or no. 52% said yes, that means it's more than five, and more than five said no. So why don't we just do the whole problem, right? Let's just do the whole problem. So Z is, we know it's 0.52. And we want the claim is most. So the claim is most, that means it's 0.5 is a yes. 0.5 is a yes times 0.5, which is the no, over the 926. This is how we get our Z statistic. So 0.52 minus 0.50 divided by parentheses, and then I need the square root symbol. 0.5 times 0.5 divided by 926. And you'll see I have 1.22. Now, we can do this on StatCrunch as well. We can do this on StatCrunch as well. So how can we do the whole thing? Well, first, how do we get the Z-score? Well, we want this to be 95% sure, right? So we know it's got to be a what? Bigger than 1.64. Well, 1.22 is here, so we know it's not significant. If it was here, we'd be good, but we're not. So we already know this is not significant. That's from the p-value, but let's do it the other way. So we're going to go to stat. I'm going to go to proportional stats, one sample, the summary. All right, so it doesn't give us the number of successes, but I know it's 0.52 of 926. So 0.52 times 926, that's how many we said right. We can't have 481.5 people, so that's 482. The number of observations was 926. It's 0.05, and we just want it to be more than that. We click. All right, Z stat 1.22, very close. Is this less than 0.05? Nope. So this is the other way of showing it. That was the whole thing. 0.124, 0.10, it's not less than 0.05, so we reject it. And we can use the exact value here instead of the 0.52. And that's what, so if we use not the percentage, right? If we don't use the percentage, this is what they're saying it's a little off. So instead of 0.52 here, if I use what they wanted, 482 over 926, I get the exact amount that's not rounded. So that's why it's close to the computer. So if I put another parenthesis here and I put 482 divided by 926, I should get their fancy exact value. See, 1.25. Ooh, okay, this is why. So I gotta be there. Yeah, I got 1.25. 1.248, which is 1.25. That's what I got. Which is totally fine. Oh yeah, 1.25. Cool. So either way that you slice it, it's still not going to be significant. They want us to use this exact value. It's close. I think we're close enough, but that's how they got that answer. All right, if it's left area, it's the area to the left. Ours was one-tailed. If it was right area, it's the area to the right. But if it was two-tailed, what we would have to do with the StatCrunch, we would have to double this value. And if we doubled this value, we'd be good to go. Our p-value is 0.0149. Okay. Now they say if they use the table for 1.25, we'd also get this value. So we might as well look at the table and make sure we get that value too, in case you hate the computer and you like the tables. Our z-score is 1.25. So here we go. It's 1.25 is right here. 0.8944. 0.8944. And as long as I do 1 minus this, I should get the value. And here's the point. This is the p-value. Ta-da! 0.1056. Either way, this is not less than 0.05, so we know we will fail to reject the null hypothesis. All right, let's keep it going. I'm assuming there's other stuff in here. And this is what I did. So we're here at 1.25. Our p-value is here, but we're not different. We have to be different. Chapter problem solution. All right, now we get to the critical value method. The critical value method of hypothesis summarized in 8.1. Our t statistic is 1.25. Our alpha is 0.05, and this is 1.645. So what does this mean? Our test statistic is here, this 1.25. That's what we got. But we have to be bigger than the 1.645. That's like what I showed you, actually. This is exactly what I showed you. See, we're here, but we got to be here. And that's why we have to fail to reject the null hypothesis. All right, and this is the one method I haven't done, which is the confidence interval method. But honestly, you pick which way works for you. If a test question says specifically use a method and you use the wrong method, I'm probably not going to take off points, but if it's on the Pearson one, they will. So guess what? We made it to this one. All right, so the claim is most internet users can be tested with a 0.05 significance. So, okay, so we have this 0.05 significance. I've never done this one, so if I mess up, bear with me. So our confidence interval is going to be 90%. Okay. 90% confidence interval estimates the population proportion P is found using the sample data. Okay, so we have N is 926, X is 482. Oh, and we just go back to this. Okay, so using the methods for 7.1, we get this. Now, what I'm going to do is I'm going to go back to 7-1. I'm going to show you exactly how to get that again because it doesn't tell you, which I hate. So let's go back to 7-1 and get the right answer. Well, we got our z-score. The only thing we don't have is the error. Okay, so we need the error. We got the z-score already, so this is the one piece that we don't have. So it's the critical value times the root p times q over n. Okay, so that's what we're gonna do. Oops. I don't like when the book doesn't give you all the information. So here we go. So I'm going to go back to 8-2. The formula for error is what? It's our z-score, alpha divided by 2. And then we have, oh, well, I'm just going to open another one so I have it next to it. And these are different claims. Like the one is like we're just saying yes or no, right? But now we're going to say we're 90% sure it falls in this range. So it's like a different answer that we're getting doing this. So we know what the answer should be, but let's get the exact one that they want. So I'm going to go back to 7-1 over here. And I'm going to pull up the formula. So we have the formula right next to it. I'm pushing this laptop probably as hard as it's ever been pushed. All right, so here we go. So we have the zeta of alpha over 2. We need the error. That's what we need to find. It's 0.05. That's 0.025 on both sides and pull into the side. So that's how we get that value. And here's the formula. All right, so that's the yes, that's the no. Oh, this is going backwards. That's how you get the n, sorry. That's confidence interval left, confidence interval right. Here's the formula. So it's PQ over the square root of what? Of n. Okay, so we already have the critical value, right? We've already got this z critical value. We've got yes or no over it. So let's see what our values are. I want to be 90% confident. Okay. So this is 482 over 926 times we can try to be as exact as we want. And this is 444 over 926. We're going to put this over 926. And I believe to get our critical value, we should have it previously, right? We already get it. Yeah, we already know it's 1.25. Oh, but this is for the specific one. So I believe they said that we want this at 90%, I believe. So yeah, we want it at 90%. Okay, so all I have to do is go back to the StatCrunch, make this 90%, 1.28, but I have to cut it in half because I want half from each. I actually have to have this from the other side. So I believe it's going to be 1.64. I believe that. If not, I did it wrong, and we'll see why. So let's do the formula. So it's 1.64 parentheses, parentheses. I need a square root over here. So it's going to be 482 divided by 926 times 444 divided by 926. And then this whole thing, we're going to divide it by 926. And this means my error for this one, I believe, is going to be 0.027. Now we have these two values, right? There's our mean in the middle. We're going to be 90% sure it's going to fall between these two values. So our mean was 0.52. So I have to subtract 0.027 from 0.52. 0.52 minus 0.027. And I got 0.493. Then I have to add 0.027. I got 0.547. And let's see if this is the right answer. Are we 90% sure that it falls within this range? 0.494, 0.48. Did I round them wrong? Oh yeah, I should have the extra one. I'm totally fine with it though. That's how you do it. So cool. All the steps. How do we get this one? Well, it was 90%, so we actually had to go 5% more because we just went it from the one side over. This is the yes, this is the no, this is divided by, this gives you your error. And then how do we do the error? We just add and subtract the error from both sides. Alternative methods, which we are going to skip because I don't think we need it. Yeah, because they don't have us do, because it says 8-5 and we're not doing 8-5. Well, we could look at it anyway. The claim given in the chapter problem most uses this, can be tested using the resampling methods. The preceding discussion illustrate the method about a proportion, and those are right tail testifying is a left tail test. Okay. The original is this, the opposite is this. Does not contain inequality. We got this for the null and that for this. Because the claim involves proportion. We use the hypothesis testing results. Okay. They talking about bootstrapping and stuff, but I might as well just do the problem. And I believe this is the last one for this one. So this is example 1 about sleepwalking. So 29.2%, I believe this is our p hat. So this is the chance of what we want is yes. So the no is going to be the other side. I'm just going to put in all the information as I get it. 100 minus 29. Oh, wait, we don't need to do that. Sorry. We just need to know the testing. They want fewer than, so we're on the other side. So our hypothesis testing is that our population, right, that this population parameter, or our, you can think about it just as the percentage is going to be equal to 0.30, and our H1 or HA alternative hypothesis want fewer than it, so it's going to be less than 0.30. So our P is 0.30, which makes our Q 0.70. We want to use a significance level of 0.05 to solve it. Okay, so I'm just going to do this without the other pieces and just see how it works out. Nice. Everything's looking good so far. So let's just do this problem and we'll see how we get it. I'm going to put this directly into StatCrunch so I don't have to think too hard about it. And let's edit this. So my number of successes. We don't have the number of successes. Oh wait, how big is my sample? I guess I didn't put it in. So my n is 19136. So I'm just going to multiply by this to get the first value for the number of successes. So 19136 multiplied by 0.292. This means our actual value of number of successes is 5588. You always round up with people. You can't have 70% of a person. I don't care how small they are. So 5588. My number of observations was 19136. Our hypothesis testing, our P is going to be 0.3. And then we want to make this not bigger than 0.3, but less than 0.3 or 30%. I want to see the critical value too. We're doing it at 0.05. Here we go. 0.008. This is significant. We can say this is significant. Our T statistic is negative 2.4. Critical value is negative 1.644. I'm going to say it's significant. Nice. Let's see if our StatCrunch looks like theirs. 5588, 19136. Sample 0.292. Standard error 0.003. Z-stat. Hey, they don't do the critical value. I always want to see that critical value because this is what I could get by hand. That's why I always want to see it. And this is how we can get that value by hand, the negative 2.41. So if you want to see me get this by hand, it's not too crazy because we already have everything set up for us right here. So we know this is going to be 0.292. We know this is going to be 0.3. We know that this is going to be 0.3. We know this one's going to be 0.7. And then we have our total, which is what? 19136, negative 2.41, negative 2.41. So there's the example. I don't know why they wanted to do it with bootstrapping or something, but that's fine. Critical value method. We know we got negative 1.645. So using critical value method to the hypothesis, we would see that in step 6, Z is negative 1.645, which we can get from the table. Well, let's see. Oh, so now I have to go the other way. Well, negative 1.645. Yeah, that's the 95% because we want to be here. That's how we can get that value. So if we want 95% going the other way, we get this negative 1.645. And our T statistic is negative 2.41, which you can see. Whoa, sorry. Which you can see it's obviously over here. So it's in the range that we want. Because it's in the range that we want, we're good. We're good to go. And now to do the confidence interval method, which I will show. So here we go. Here's the confidence interval method. 1.64. We know the first one is the first one is 0.292, which makes the other side one minus 0.708. This is just to get the error. 1.64, 0.292 times 0.708. And then the whole thing is divided by the total, which is 19136. This is how we're going to get our error. We'll divide this by 19136. So we have this value of 0.00539. Our error is 0.005. So what does that mean? We know that this mean, this average, right, is this 1.64. So all I have to do is take that and add the 0.005. Sorry, it's 0.292 is our mean, and we just have to subtract this and add this. So all I have to do is take 0.292, add 0.005, so 0.297 is the one side, and the other side is 0.287. That should be our answer. Let's see. If I made a mistake, you know, it happens. 0.287, 0.297. We got it. We got it. So we're 90% confident that our answer falls within this range. Sweet. Let's keep it going. All right, so we made it all the way to part 2 of this video. Hopefully that was useful. I did the problem not once, not twice, but 3 different ways, the 3 ways they showed. One was using the p-value, one was using the critical value, and one was using what? The confidence interval. So now part 2 says, oh yeah, this is the end. I was just curious how much more there was. Part 2 says the exact methods for testing claims about population proportion P. Instead of using the normal distribution as an approximation, a binomial, we can get exact results by using the binomial probability distribution itself. Wild. Binomial probabilities are a real nuisance to calculate manually. Okay, but technology makes it quite simple. Also, this exact approach does not require having more than 5 of each. Okay, so we can do this by hand, even though it's going to be annoying. All right, so identify the sample size n. It's the number of successes. So left is p-value is equal to p. This is for x or fewer samples. So identify the sample size n, and then find the p-value by using technology to find the binomial probabilities. Note there is no universally accepted method for the two-tailed exact case, so this can be treated with other approaches. Okay, so you can only really do this for left and right-tailed test. All right, so let's actually try this. In example 1, we have an n, which is 19,136, and 29.2% of them, or 5588, was a yes, which means the other side is the no. And we want to use hypothesis significantly less. So if we use hypothesis significantly less, here we can use a binomial probability distribution to find the probability of getting 5,588 or fewer sleepwalkers. So still our hypothesis 0 is going to be, this is equal to the exact amount. So 5,588. And your hypothesis A is going to be, this value is going to be fewer than 5,588 or fewer. I think it just has to be fewer based on this thing. All right. Oh, well, they just want it to be the same to start, so I might as well just write it how they have it. So H0 is B is equal to 0.3, and HA is P is going to be less than 0.3. The statistics results showed it's 0.008, so we ended up getting a probability which is less than 0.008. At least it's extreme. Okay, given the p-value is that, we rejected the null. Because we did sample that. So support the alternative hypothesis. Okay. Proving the exact method of criticism is that it's too conservative in the sense that the actual probability of the type 1 error is always less than or equal to A. It's going to be lower than A. But the exact method, the actual probability of a type 1 error is less than or equal to alpha. All right, so we do a simple continuity correction. Proves the conservative behavior of the exact method with an adjustment to the p-value. But how did we get this? There's choice for exact probabilities. What's that? No, it doesn't really give us that. All right, so maybe we can't do it. So P is fewer is 1/2 exactly X. All right, so I'm just going to skip those. I'm going into what it says. Okay, one sample with summary, enter this. Yeah, okay. So we're ready for the questions. I wouldn't worry about the end too much. So let's try 1 through 4, 6, 7, 12, 13. 4, 6, 7, 12, 13. All right. In exercise 1 through 4, the results from the Hankook tire gauge index. All right, so our sample. So this for number 1, we have our sample, which is 1,020 adults. Our sample population said that 86% said they were great drivers. And we're trying to do the claim that 0.75 are good drivers. That's what 3/4 is. And that makes Q 1/4 or 0.25. Identify the exact number of respondents who rated themselves as above average drivers. So here's the first step. They want the exact number. Nothing too crazy here. I'm going to do, oops, I'm going to do 0.86 times the total, which is 1020. So for A is the total, so it's going to be N times P. So what is this? 0.86 times 1020, and we get 877.2, but we always round up because why? You cannot point to a person, so it's 878 is the first one. Identify the sample proportion and use the symbol that represents that. The sample proportion is 0.86. All right, C. Identify these. Oh, okay. So basically, your null hypothesis is going to be P is equal to 0.75, and it's more than. So our alternative hypothesis is going to be P is greater than 0.75. Ta-da! Oh, well, I already did that. So now let's find the test statistic. So to get the test statistic, we can do that formula that I did above, but you just watched me do it not once, but twice. So we might as well do what? We're just going to use StatCrunch for, this is number 2. To get this test statistic, we're just going to use StatCrunch. I'm just going to change the options. My successes is 878. My observations is 1020. We want this to be 0.75, but we want this to be bigger than 0.75. And we want to show the critical value because that's the value we want. We click compute. It's significant. Here's our z-stat, so our z statistic. is equal to 8.17. That's the answer to 2. Identify, okay. Are the requirements satisfied? Well, yes. Why is it? There's more than 5 P's, there's more than 5 Q's, because 25% of 1020 is more than 5. It's a yes or no answer, and they're independent. So 3 is yes. I'm going yes. 4, regardless of the conclusion, reach from that. Is it possible that? So, okay, A is yes. What is B? Okay, so they're telling me, so the one that's not equivalent to the other two, the confidence interval is not equivalent to the other two. All right, C. If the null is low, it must go because we got something less than 0.05 here. So less than 0.05 or 0.01, depending on your alpha. You reject the null, which means we found a difference, which is nice. Let me see what the other questions are. D, another memory trick is hi, the null will God, I don't know. I'm skipping this. You can do that part yourself. E, common significance are 0.01 and 0.05. Why would it be unwise to use a significance level? Because it's too specific. It makes things more challenging when you're doing the numbers. It makes it harder to see. To me, that's E. Why you use that? Because you want something that's consistent, 95%, 5% likely chance. When you have something with this many significant figures, people can get confused. All right, well, that's 1 through 4. Let's go to 6. Here is 6. Identify the values, use the normal distribution, use 0.05. Okay. Okay, here's 6. Is it two-tailed, left-tailed, or right-tailed? So that's A. So this is what they give us. This is one-tailed because this is not equal to 0.25. So A is one-tailed. Let's see what they want for B. What is the test statistic? It's right here. So Z is 2.21. That's our test statistic. What is the p-value? See, the p-value is 0.0132. Sorry, I keep getting emails and it's slowing me down. Question about homework, I'll do it after this one. Okay, let's go to D. What is the null hypothesis? The null hypothesis is that P is equal to 0.25, which means 1/4 of people have no lock screen. So that's the null hypothesis. 1/4 of people have no lock screen. And let's look at what E says. What is the final conclusion? It is greater than 0.05. So E, we reject the null. We reject the null and we can say that we are 95% certain that more than 1/4 of people have no lock screen. Ta-da! And that was all the parts. And you can write the final conclusion. I'm fine with that. All right, so that was 6. I said I was going to do 7, 12, and 13. So let's go to 7. All right. It's one-tailed. Okay, B is was the test statistic. I believe it's got to be this negative 6.32. I don't use Minitab, so you know what I'm gonna do? I'm actually gonna do it myself. Feel free to do it yourself. If they're giving you something weird and it doesn't make sense, just do it yourself. So we're gonna edit this. It says 40% of 1,000. So the first thing I got to do is figure out what 0.40 times 1,000 is. I know that's really simple, but I'm always trying to show you every single step. So that's 400. Okay, and our total is 1,000. And we have, it's a 50-50, so that's a 0.5. And we want to be less than 0.5. And significance of 0.05 compute. Oh, I forgot the 0 for the 1,000. And here's the answers. So the C statistic is negative 6.32. I just like to double check. So I was right. But notice that I just put it into StatCrunch and I got the same answer. What else do we need to do? What was C? Oh, it's the p-value here. It's less than 0.0001. Our null hypothesis is p is equal to 0.5. Alternative hypothesis is that p is less than 0.5. And this is, we can reject the null. I'm gonna let you guys write this statement. All right, so that was 7. All right, let's look at 12 and 13. Maybe that'll be more challenging, but this seems pretty easy to me. 12 and 13. All right, so here's 12. What do we have to do for these? Null, alternative, CTAC, p-value, critical value, conclusion, as well as the final conclusion. All right, I'll just do 12. You can do 13 yourself because the answer's in the back of the book, but I'll do 12. This will be the last one I do. We got M&Ms. N is 345. This p hat is 25.5%. And we want to say that the exact amount is 24% for these delicious blue M&Ms. So this means our null hypothesis is that p is equal to 0.24. All right, and this, we got a two-tail. So our alternative hypothesis is that it is not equal to 0.24. It doesn't say it, right? It doesn't give us this. So I'll do everything but the statement. This is pretty much everything we need. So our options, edits. So if it's 0.24, sorry, this is our test statistics, so 25.5 out of 345. 0.255 times 345. That's 87.975. So we round this up to what? 88 successes. We've had 345 successes. The hypothesis testing is 0.24. And we want to just not equal it. Notice that changes a lot of stuff. We compute it and we have everything. It's not significant. This is more than 0.05. So this is everything. So our z-stat is 0.656. Our critical value is 1.96. And our p-value, this is the only thing that I really look at. You can do it all three ways, like I did above, but the p-value is 0.5121. So we fail to reject the null. And what were we trying to say here? So we accept the null. What does accepting the null mean? We are 95% sure there is 0.24 percentage of blue M&Ms in it. That is the answer to 12. Try the rest yourself. Gonna be just fine. I know you'll be okay. Let me know if you have questions, and good luck.